Okay, so here's the last lesson of the week. This is objective 10.2c. We're going to be solving some more trig equations, but today's equations will have mixed functions and will be in restricted intervals. So at least there's that. We don't have to find all the solutions, just a handful of solutions. Our objective here is to use our trig identities. Your exact value trig sheet would be super useful. Graphing calculator, I would suggest Desmos since you're working on homework at home to solve trig equations. Okay, so a couple notes. When a trig equation involves more than one function, if you can use a trig identity to rewrite the equation in terms of only, say, sine or cosine or tangent, it's really helpful. But I'm just going to highlight here with my mouse that when you're using trig identities to assist, you have to check for extraneous solutions because they sometimes will create extra solutions. I'm going to suggest that you use Desmos to check your math today because Desmos will help you see when you have a solution that is extraneous. Okay, some trig identities that you'll need for today's notes. You get your Pythagorean identities, sine squared x plus cosine squared x equals 1. And of course, you can rearrange that, solve it for sine squared x or cosine squared x. And tangent squared x plus 1 equals secant squared x. I don't think on your homework, I might have given you one on your homework where you'd use the cotangent squared x plus 1 equals cosecant squared x. So make sure that you have those available. Also, your double angle identities, the ones for your notes today you need are sine double x equals 2 sine x cosine x, and the cosine double x equals 1 minus 2 sine squared x. However, there you might want to use the other. Remember, cosine double x has two other options, and so you might want to use a different option when you're doing your homework. So make sure you have your trig identities out. Another set of identities that you might want to use is your cosine x or your reciprocal identities, any of those, but you have those memorized. Okay, so let's take a look at this first equation. We have example 9 here. And so what I'm going to do is show you how to solve this algebraically, and we'll use the unit circle to solve it. And then we'll go to Desmos and we'll graph it to solve it and check our solutions. So here this equation is sine of beta plus cosine beta equals 1. And I can't really decompose this into sine and cosine. And I can't really change sine of beta to cosine or cosine beta to sine. Now they do exist in the same Pythagorean identity where it's sine squared beta plus cosine squared beta equals 1. And that might be useful. That might let me solve this equation. So let's try that. Let's go ahead and just square both sides of this equation. So we're going to square sine beta plus cosine beta, and we'll square 1. Okay, so that was square both sides. Now, something that I have to reiterate here is when you change an equation like this, sometimes that creates extraneous solutions. So when you get all your solutions at the very end, you have to plug them into the original equation to make sure that that they're not extraneous solutions. So we're going to expand this out and multiply sine beta plus cosine beta, quantity squared. So that's sine beta plus cosine beta times itself equals 1. And then we'll just multiply that out. And I'm just going to do that real quickly here. It's not like you guys haven't squared quantities before. So that's sine squared beta plus sine beta cosine beta plus sine beta cosine beta is 2 sine beta cosine beta plus cosine squared beta equals 1. Okay, so there we have that. And it looks way more complex now. However, look here, we have a Pythagorean identity here, so we can replace sine squared beta plus cosine beta with 1. All right, so we have 1 plus 2 sine beta cosine beta equals 1. And what did we do there? We used a Pythagorean identity substitution. Again, we used a substitution, which means an identity substitution, so we're going to have to check our solutions. So I'll subtract 1 from both sides, and we get 2 sine beta cosine beta equals 0. And here we just have three factors here, 2 times sine beta times cosine beta equals 0. So that means either sine beta has to equal 0 or cosine beta has to equal 0, or both of them have to equal 0. So we'll just say we'll use the principle of zero products. Sine beta equals 0 or cosine beta equals 0. And we'll go, all right, so sine beta, remember that represents your y coordinate. So your y coordinate is 0 here at 0 radians, and we are in 0 to 2 pi, so 0 radians, and over here at pi. So we could say that beta equals 0 or pi, and cosine beta equals 0, and that's your x coordinate. So when your x coordinate equals 0, you're here on your unit circle, and so that would be at pi over 2, and that's a positive one there. And then down here, you're at 0, negative 1, and that would be at 3 pi over 2. So our solutions for cosine beta, beta would be at pi over 2 and 3 pi over 2. All right, so there's two ways you could go about checking your solution. You could just start plugging all of these values into the original equation and making sure that when you add the two values, they equal 1, or we'll go to Desmos here. So I'm going to open up Desmos. And here in equation 1 and 2, I'm going to use the intersect method where I'm setting each side of the equation, sine x plus cosine x equals 1, setting each side of the equation equal to 1. And you'll notice that I have restricted the interval here so that I'm only graphing from 0 to 2 pi, double checking that I am actually in radians, okay? And I'm going to use the intersection method. So you can see that they intersect here at 0 radians. They intersect at pi over 2. But at pi, they do not intersect. And at 3 pi over 2, they do not intersect. So we have two solutions that are extraneous. So when I go back here, we're going to have to throw out pi and 3 pi over 2. Now let's see why that's actually the case. So we're saying that the solutions are 0 and pi over 2 according to Desmos when we check. So why, doesn't pi work? Let's check. So we'll do sine of pi plus cosine of pi is supposed to equal 1. That's our original equation up here. Well, the sine of pi is 0. Okay, so sine of pi is 0. But cosine of pi is negative 1. And 0 plus negative 1 is not 1. So that solution is no good. Same thing would happen if we were to do sine of 3 pi over 2 plus cosine of 3 pi over 2 equals 1. So if we go to 3 pi over 2, your sine is negative 1 and your cosine is 0. And that also does not equal 1. So those solutions are extraneous. So your final solution here is 0 and pi over 2. All right, moving on to example 10. So here with example 10, you have solve cosine double x plus sine x equals 1 in the restricted interval 0 to 2 pi. So we're in radians here. And here we have a double angle. And so, but cosine 2x can be written in terms of sine only. I'll go back up here. So cosine 2x, I can use 1 minus 2 sine squared x. It's an identity. It's always true. So I can replace cosine 2x with 1 minus 2 sine squared x, and then plus sine x equals 1. So what did I use there? I used a double angle identity. That's a D, not a P. A double angle identity replacing cosine 2x with 1 minus sine squared x. Okay, so now we'll simplify that. I'll grab my black pen here. We'll simplify that equation here. I'll subtract this one to this side. So we get negative 2 sine squared x plus sine x equals 0. And if you want, you can use your substitution where we let sine x equal a. It's up to you. So we'll do negative 2a squared plus a equals 0, and use your factoring here. We'll factor out You could factor out the negative. I tend to like to factor out the lead negative, so I'm going to factor out a negative a, leaving me with 2a minus a divided by negative a is negative 1 equals 0. So we know negative a equals 0 or 2a minus 1 equals 0. So a equals 0 or a equals, add 1, divide by 2, 1/2. So we'll go ahead and substitute back in now that we've solved for a, sine of x. So sine x equals 0 or sine x equals 1/2. So remember, sine x again is your y coordinate. So y equals 0 here on your unit circle at 0 radians, and over here at pi radians. And sine x equals 1/2. Remember, that's your y coordinate. So we're going to go up here to 1/2. So that would be this angle right here and this angle right here. So we're looking at pi over 6 and 5 pi over 6. So we could say x equals 0 and pi, or x equals pi over 6 and 5 pi over 6. And because we used a substitution here of an identity, we have to check those solutions. So again, you could algebraically just check them if you want to, or we can go to Desmos, and I will just turn on. Again, I'm going to use the intersect method here. I set the left side of the equation equal to y and the right side of the equation equal to y over the restricted interval here. And we'll just click on their intersection. So at 0, pi over 6, 5 pi over 6, and pi, this is where the two sides of the equation agree and have the same solution. And so we can see here that we don't have to throw out any solutions. None of them are extraneous. So we'll write out our answer in least to greatest radians, least to greatest. So 0 pi over 6, 5 pi over 6, and pi. And I'm going to put a little box around that. There's our solution for that one. Okay, next one. All right, so here we have example 11. It says, solve tangent squared x plus secant x minus 1 equals 0 in the interval 0 to 2 pi radians. Okay, so this is definitely written in two different functions here, but tangent squared x and secant squared x exist in the same Pythagorean identity. Remember that tangent squared x plus 1 is equal to secant squared x. And so I could rewrite tangent squared x in terms of 1 and secant squared x, and then my equation would only have secant in it. So I'm going to go ahead and solve this for tangent squared x. So we would subtract 1 to the other side. So tangent squared x equals secant squared x minus 1. So I could make a substitution here for tangent squared x and rewrite it as secant squared x minus 1 plus secant x minus 1 equals 0. And then combine your, and let me write down that I used a Pythagorean identity there. So that was a Pythagorean identity. And since I made a substitution, it means I have to check my solutions when I'm done. And I'll just go to my black pen here now. And we will combine like terms. So we get secant squared x plus secant x minus 2 equals 0. And at this point, if you would like to make a substitution for factoring, we could say that we're going to let secant x equal a and make that substitution. So a squared plus a minus 2 equals 0, and do your factoring here, looking for the numbers that multiply to -2 and add to 1. That one's a pretty simple one. So a plus 2 and a minus 1 equals 0. So you can see here that a equals -2 or a equals 1. And then we'll go back in now that we've solved and found our zeros. We'll resubstitute in our secant x for a. So secant x equals -2 or secant x equals 1. And again, you have your exact value trig sheet. You could look down that list of secant x equals -2, or you could use a reciprocal identity and just, so if secant x equals -2, then cosine x equals -1/2, and cosine x equals, flip the 1 over, it's 1. Then go to your unit circle here to cosine x, which is your x coordinate here, is negative 1/2. That would be here. So that would be this point up here where x is negative 1/2 square root of 3 over 2, and then down here. All right, so that would be 2 pi over 3 and 4 pi over 3. So our solutions there would be x equals 2 pi over 3 and 4 pi over 3. And then cosine x equals 1, so our y coordinate would be 1, and that would be here at 1, 0. And so that would be at 0 radians, so x equals 0. And then before we decide that those are all the solutions, we'll go into Desmos to double check and look at the graph. And we're going to use a zero method here because when we type this in, it's all on the same side of the equation. So what we want to see is when does it cross y equals 0. So that would be this equation here where we have tangent squared x plus secant x minus 1. And you're looking for your intersections here at 0, 2 pi over 3, and 4 pi over 3. Not including 2 pi because 2 pi is restricted from our interval. And so we'll keep all our solutions. So x equals 0, 2 pi over 3, and 4 pi over 3. And there you go. Okay. And last one. So here we have example 12. Sorry about that. It says solve sine x minus cosine x equals cotangent x. And you know what we're missing in the interval 0 to 2 pi? So add that in there. I don't know how that didn't get typed in, but you know, I make mistakes. Okay, so first of all, this is an ugly equation. It's got 3 different trig functions in it, and I could decompose cotangent into cosine of x over sine of x, but then that introduces a fraction and it just makes it really difficult to solve. So, and I sat and I messed with this problem and so I tried to solve it algebraically, and it took me like 5 minutes, and so it would take you probably even longer. So my suggestion is here, if you grapple with a problem for a little while and you're trying to solve it algebraically, 4 minutes into it, if you can't see your way to the answer, that's okay for now. Just go ahead and don't feel defeated or anything. Just understand that sometimes these can't be solved algebraically. In fact, let me think back. Let me look at my notes. Did I solve this one algebraically? I don't think that I did. So I definitely went to my calculator, so don't feel defeated, okay? So let's see. Let me turn off our last graph here. And so this was the left side of the equation, and equation 6 here, sine x minus cosine x over our restricted interval, and then here's cotangent x. And so if I wanted to find the solution for that, I would just say, okay, they share an answer at 1.128 radians and at 5.661 radians. So I could draw that picture. And so on your assignments today, or when you're working on your assignment, if you can't find your way to the answer algebraically, it is okay for you to draw the picture of the graph and then give me the solutions from the graph. But I do need to see some work. For every single problem, I need to see some work. And I do need to see some effort for solving algebraically. The other way that you could do this, and my preference is always to just find the zeros. So what I did was I took the equation, split it into 2 to find the intersections. I prefer to use a zero method, so I subtract cotangent from the right side of the equation to the left. And so I prefer to draw this graph. It's a little bit simpler to draw. So here at, excuse me, 1.28 radians, and here at 5.661 radians, that would be my choice, would be to graph that. So on what you would do here is you would say you typed in y equals sine x minus cosine x minus cotangent x, and then you graphed the solution. And I don't remember exactly, so a little bit cos pi over 4, so about right there. And then where was the other one? little past 7 pi over 4. Which would be like right there. And it kind of zooms past and does some weird stuff like that. Not exactly sure. It doesn't matter because what we're looking for mainly here is the solutions. And so the solutions were 1.1280 and 5.6610. So our solutions here are x equals 1.128 radians and 5.661. So your homework tonight is to do problem 27 and then problems 31 through 37 all. And again, I would like to see your effort in solving these algebraically, but don't frustrate yourself if after a little while you can't solve them algebraically. Just go ahead and graph them and draw a picture of the graph and give me the solutions. And there you go. That's today's lesson.